There's a rule in physics, a hard rule, one that every engineer, every pilot, every scientist agrees on. And then there are 5 aircraft that looked at that rule and just ignored it. I'm not talking about going fast. I'm not talking about flying high. I'm talking about aircraft that did things that the people who built them couldn't fully explain, things that should have torn the plane apart, things that broke radar, broke records, broke the math. 5 aircraft. 5 moments where human engineering crossed a line that wasn't supposed to be crossable. Let's start with number 5. By the end of this video, you're going to know about a plane that flew so hot it had to be built with gaps in its own body. A helicopter that should have shaken itself to pieces, but didn't. An aircraft that was invisible not just to radar, but physically impossible to look at directly from certain angles. A bomber that costs more than its own weight in gold. And number 1, a plane so fast that when missiles tried to chase it, the pilots didn't even bother evading. They just pushed the throttle. Here's where it starts. Number 5 is the V-22 Osprey. And the reason it's on this list is simple. It should not work. Here's what the Osprey does. It takes off like a helicopter, rotors pointing straight up, lifting vertically. Then, once it's airborne, those same rotors tilt forward 90 degrees, and suddenly it's flying like a conventional aircraft. Faster, further, more efficient. Sounds great. Here's the problem. The physics of helicopter flight and the physics of fixed-wing flight are not just different. They actively work against each other. The rotor size you need for a helicopter is completely wrong for a plane. The weight distribution that works for one destroys the other. Engineers in the 1970s ran the numbers and said flat out, a practical tiltrotor aircraft cannot be built. They weren't wrong. The early prototypes were disasters. Vortex ring state, a condition where the aircraft essentially falls into its own downwash, caused crashes that killed test pilots. The transition between helicopter mode and plane mode created vibrations so violent that components cracked mid-flight. And yet, the Marines fly it. Special operations use it. It carries 24 troops at 316 miles per hour, faster than any helicopter alive, and lands in places no fixed-wing aircraft can reach. The engineers didn't solve the physics problem. They engineered around it. The fly-by-wire computer system makes 40 corrections per second to compensate for the instability that should, theoretically, be tearing the aircraft apart right now every time it flies. 40 corrections per second. Without that computer, the Osprey is an aerodynamic disaster. With it, it's one of the most capable aircraft on the planet. That's number 5. A machine that works only because a computer is constantly preventing it from destroying itself. Number 4 is different. Number 4 didn't need computers to break physics. Number 4 needed something far stranger. The SR-71 Blackbird flew at Mach 3.2. That's 2,200 miles per hour. New York to London in under 2 hours. And at that speed, something happens to metal that engineers weren't sure how to solve. It melts. Not dramatically. Not all at once. But the friction from flying that fast heats the aircraft's skin to over 300 degrees Celsius. Aluminum, the material every other aircraft is made from, starts deforming at those temperatures. The plane would warp, crack, and eventually tear apart. So Lockheed's Skunk Works team used titanium instead. 93% titanium. The most titanium-heavy aircraft ever built. And here's the part that sounds like a mistake but was actually genius. They built it wrong on purpose. At room temperature, the SR-71's panels didn't fit together properly. There were visible gaps in the airframe, gaps you could stick your finger into. On the ground, fuel leaked out of the wing tanks onto the runway, every time. Because the engineers knew something. At Mach 3, the airframe heats up and expands. Those gaps close. The panels lock together into a perfect airtight structure, but only when the plane is doing what it was built to do. It was a machine designed to be broken on the ground and perfect in the air. And the engines. The engines on the SR-71 are technically ramjets at high speed, meaning at Mach 3, they're not burning fuel in the traditional sense. The inlet compression alone heats the incoming air to the point where combustion becomes almost self-sustaining. The engineers called it an isentropic spike inlet. The pilots called it the most terrifying sound they'd ever heard when it worked correctly. Over its service life, the Soviet Union fired over 4,000 surface-to-air missiles at the SR-71. Not one came close. The standard evasion maneuver was to push the throttle forward. That's number 4. A plane that was physically broken until it hit Mach 3. Number 3 is a different kind of impossible. Number 3, the B-2 Spirit stealth bomber. The B-2 has no tail, no vertical stabilizer, no rudder. Every other aircraft in history uses a tail to control direction. It's as fundamental to flight as wings. The tail is how you steer. The tail is how you stay stable. Remove it, and aerodynamics says your aircraft immediately begins a flat spin and crashes. What it has instead is a fly-by-wire system so complex that the aircraft is technically in a constant state of controlled instability. 4 flight computers run simultaneously, and if 3 of them agree on something, that's what happens. No single computer has full control. The system is designed to disagree with itself, because an aircraft this unstable needs constant cross-checking to stay in the air. But here's what makes the B-2 truly strange. Its flying wing shape isn't just about stealth. It creates a phenomenon called span-wise lift distribution, where the entire body of the aircraft generates lift, not just the wings. In theory, this is incredibly efficient. In practice, it makes the aircraft want to rotate, pitch, and yaw simultaneously in ways that no human pilot could correct fast enough. The computers correct for it 40 times per second, same as the Osprey. Different problem, same solution. Let the machine fight the physics so the pilot doesn't have to. Cost per aircraft, $2.1 billion. There are 20 of them. If you took the weight of a B-2, 160,000 pounds, fully loaded, and replaced every pound with gold, it would cost $4.8 billion. The aircraft costs less than that. Barely. Number 2, the U-2. And this one breaks physics in a way that nearly killed every pilot who flew it. The U-2 flies at 70,000 feet. That's above 95% of Earth's atmosphere. At that altitude, the outside air pressure is so low that human blood begins to boil at normal body temperature. Not metaphorically, actually boil. The pilots wear full pressure suits, essentially early spacesuits, because without them, they would die within seconds of cabin depressurization. But that's not the physics problem. The physics problem is what happens to the aircraft at that altitude. At 70,000 feet, the air is so thin that the difference between the U-2's minimum flying speed and its maximum safe speed, what pilots call the coffin corner, is less than 10 knots. 10 knots! That's about 11 miles per hour. Go 1 knot too slow. The aircraft stalls and falls out of the sky. Go 1 knot too fast. The aircraft exceeds its structural limit and breaks apart. The margin for survival is a window so narrow that pilots described it as flying on a razor's edge for 9 hours straight. And the landing. The U-2's glide ratio is so extreme, meaning it loses altitude so slowly, that landing it requires a chase car on the runway driving at 100 miles per hour, with a second pilot screaming altitude corrections over the radio because the aircraft is physically difficult to land from inside the cockpit. Every single landing. Which brings us to number 1, the North American X-15. And I want you to understand something before I tell you what this aircraft did. It is not a jet. It is not a plane in any conventional sense. The X-15 was dropped from a B-52 at 45,000 feet, fired its rocket engine for 80 seconds, and climbed to the edge of space. On its peak flight, it reached 354,200 feet, 67 miles above Earth's surface, high enough that 3 X-15 pilots were awarded astronaut wings. Its top speed, Mach 6.7, 4,500 miles per hour. At that speed, the aerodynamic heating on the nose of the aircraft exceeded 1,200 degrees Fahrenheit. The pilots described a pink glow visible through the cockpit windshield. The air in front of the aircraft was so compressed, it was literally glowing with heat. And at the top of its arc, At 67 miles altitude, the control surfaces stopped working. There is no air up there. Ailerons, rudders, elevators, all useless. The X-15 used hydrogen peroxide thrusters to control orientation, the same technology used on spacecraft. It wasn't flying anymore. It was in ballistic spaceflight, falling back toward Earth, correcting its re-entry angle with rocket thrusters, hitting the atmosphere at a precise angle. Too steep and it burns up, too shallow and it skips off into space. And here is the twist. Every technology in that list, the tiltrotor computers, the titanium expansion joints, the flying wing instability, the coffin corner protocols, the re-entry thrusters, every single one of it was developed, tested, and proven on these 5 aircraft before anyone had decided to go to the moon. The engineers weren't just building planes. They were writing the instruction manual for space travel. Neil Armstrong, before he walked on the moon, was an X-15 pilot. He flew it 7 times. He reached 7,500 feet in it. He learned how to re-enter Earth's atmosphere in it. The aircraft that broke physics weren't anomalies. They were the education, and the classroom was 70,000 feet. Above anyone who thought it couldn't be done. 5 aircraft. 5 different ways that human beings decided the rules weren't final. And look, I want to be straight with you. None of these engineers actually broke physics. Physics doesn't break. What they broke was the assumption that physics meant impossible. What they found every time was that impossible just meant we haven't found the workaround yet. The V-22 didn't defeat aerodynamic instability. It hired a computer to manage it 40 times per second. The SR-71 didn't beat heat. It built itself to expand into heat. The B-2 didn't eliminate the need for a tail. It distributed the tail's job across 4 computers and a flying wing. The U-2 didn't make the coffin corner safe. It trained pilots to live inside it. And the X-15 didn't conquer space. It used space, used the physics of re-entry, to teach an entire generation of engineers what space actually was. The lesson isn't that physics can be ignored. The lesson is that the people who changed the world were the ones who refused to let physics tell them what wasn't worth trying. If this messed with your head the way it messes with mine, every time I go back through this history, the subscribe button is right there. Next week, we're going into the one aircraft the U.S. government still hasn't fully declassified. And the reason they haven't is more interesting than the plane itself. I'll see you then.